So multivariable calculus, lecture 4. Okay. So I hope you are liking my lectures. Okay. So recall in the last lecture we are really on our way to define the notion of differentiability for functions on Rn. Okay. Okay. So we say that so that there is natural obstruction because if you look at this definition in the per function from R to R. So the thing is, we are dividing by an element h, but in higher dimensions, there is a we don't have any meaning of division by vector. So therefore, there is a problem. So what I'm saying in higher dimension, where we don't have meaning of division by vector, so there is natural obstruction. So the thing is, we really wanted to interpret that differentiability in a different way. So on our way, we really prove this thing. Proposition, we prove this proposition. So let U subset of R be an OS. OS means open set. Let U subset of R be an open set and let A belongs to U. And let F is a function from U to R. Then the following are equivalent. F is differentiable at A. There exists a linear map T from R to R so that limit s tends to 0 mod of f of a plus h minus f of a minus th by modulus of h 0 is equal to 0. Okay. So we have this proposition. Let U subset R be an open set. Let A belongs to U. Let and f is a function from U to R. Then the following are equivalent. F is differentiable at A if and only if there exists a linear of T belongs to so there is a linear of T from R to R, so that limit s tends to 0 mod of f of a plus h minus f of a minus th by modulus of h is equal to 0. Since look at this thing proposition very carefully. Since uh, these two I and 2 are equivalent statements, so one can take the differentiability definition of differentiability the second statement, this statement. Okay. So the thing is, if you look at the second statement carefully, so this second statement can be generalized to generalized for function from Rn to Rm. Okay, so looking at the second statement, 2i. So 2i suggested a definition of differentiation in higher dimension. So let me write that thing. Okay, so here is a definition. Definition. So let U subset of Rn be open, be an open set, and let A belongs to U. We say that a function from f from okay, we say that a function okay, no, let us say let f be a function from U to say Rm. We say f is differentiable at a if and only if there exists a linear map T from Lrn. There is a linear map T from Rn to Rm. Okay, so that limit s tends to 0 mod of a plus h minus f of a minus t of h by modulus of h, this is 0. Okay. So let U subset of Rn be an open set containing A. Let f is a function from U to Rm. We say that f is differentiable at A if and only if there exists a linear map T from Rn to Rm, so that limit h tends to 0, norm of f of a plus h minus f of h minus th by norm of h is equal to 0. So f of a plus h is a vector in Rm. So this the norm of the numerator is the L2 norm of Rm. Okay, and norm of the denominator is L2 norm of Rn. Okay. Okay. So the thing is, we say that f is differentiable at A if and only if there exists a linear of T from Rn to Rm, so that limit h tends to 0, norm of f of a plus h minus f of h minus th by norm of h is equal to 0. And the norm of the numerator is L2 norm of Rm, and norm of the denominator is L2 norm of Rn. Now, so this is so motivation for this definition is coming from this proposition 2i. Okay. Now the thing is, let us see call this star. Okay. So the thing is, so in the statement, actually we are writing that there exists a linear map T from Rn to Rm, so that this condition star is satisfied. We say that f is differentiable at A if there exists a linear map T from Rn to Rm, so that this star satisfied. So the thing is, it may happen that there might exist two different T's or more than one T which may satisfy this condition star. Okay, but we will prove soon that the thing is, if the T which will if a T satisfies this star, then T has to be unique. We'll prove shortly. Okay, so what I'm saying, so if T1 and T2 satisfies star, okay, then T1 is equal to T2. Okay, so remark, so it turns out that, so remark, it turns out that if T1 and T1 comma T2, okay, T1 and T1 and T2 satisfy star above, then T1 is equal to T2. Okay, so this linear map T1 has to be T2. Therefore, the T in star is unique. Okay, so therefore we can define this. We can define a prime A is equal to T, because since this T is unique, so I can define a prime A equal to T, and this A prime A is called derivative or total derivative or differential or total differential CL of f at A. Okay, so this, since this linear map T is unique, so therefore we can define A prime A is equal to A prime A is called derivative or total derivative or differential or a total differential of RT. Okay. So we will prove this remark shortly. So now another definition. Okay. Our definition. So suppose so I am with this condition, this thing. Suppose f is differentiable at each a belongs to a. Okay. Then f is said to be differentiable on u. Okay. So this is very natural definition. Okay. Now proof of the remark. So let us write that proposition. So, suppose T1 belongs to L, Rn, Rm, and T2 belongs to L, Rn, Rn, satisfies star of the previous space. That is previous space. So what does that mean? That is limit h tends to 0, f of a plus h minus f of a minus T1 of h by norm h. This is 0, and limit h tends to 0, f of a plus norm of a plus h minus f of a minus T2 h norm by norm h is equal to 0. Okay, so this is the meaning. So suppose T1 and T2 satisfy star, this condition star in the, then T1 is equal to T2. Okay, so let us call this as suppose I and call this as 2I. Okay. Okay, so proof is very simple. Okay, so proof let us give in the next place. This is my proposition. Okay, proof. So let T is equal to really your T1 minus T2. So what you have to show? You have to show that TB is equal to 0 for all B belongs to Rn. Okay, so T is identically 0. That will imply that T1 is equal to T2. Now this norm of TH is nothing but T1 of H minus T2 of H. I can, what I will do, I will add something and subtract something. Let us see. This is A plus H minus F of A minus T2 of H. Okay. So minus, this is the same thing as A plus H minus F of A minus T1 of H. Okay. Okay. So now the thing is, now I take the norm, both sides, everywhere. This is this, this is this, this is this. Okay. Okay. Now I can apply the triangle inequality. This is A plus H minus F of A minus T2 H norm plus this thing F of A plus H minus F of A minus T1 H norm. Okay, okay. And that will give you norm of TH by norm of H. This is less than equal to norm of F of A plus H minus F of A minus T2H by norm H. Okay. Plus right hand side is plus f of a plus h, norm of a plus h minus f of a minus t1 of h by norm h. Okay, okay. So now the look at the condition I and 2. Condition I, if you take limit h tends to 0, if you take limit h tends to 0, so taking limit h tends to 0, okay. So it says that if you take limit h tends to 0, this first quantity is 0. This quantity is 0, condition I, and this is also goes to 0 as it tends to 0, and using I and 2I of previous page. So we get this thing, norm of th by norm of h. This limit is tends to 0, this is 0. Okay, okay. Now what I have to show? I have to show that t is equal to 0. Okay. So t0 0 is equal to always 0. There is no, because t is a linear map. So as t is linear, t0 is equal to 0. This is clear. So let 0 not equal to b belongs to Rn. Okay, okay. Then limit t tends to 0. Then limit t tends to 0, tb is equal to 0. Okay, so what I can do, okay, so call this as a, so 3i, say. So from 3i, okay, so from 3i, what I will get? So in, since this limit t tends to 0, tb is equal to 0. Okay, so since this thing is 0, so from 3 actually what I will get? So from 3 previous space, previous space, we get this thing. The limit t tends to 0, norm t p norm by t b norm. This is 0. Now the thing is, this t is a linear map and norm is a homogeneous function. So I can pull this limit t tends to 0. So that will give you mod of t, norm of tb by norm of b. This is equal to 0. Now look at this thing. This mod t will cancel out from the numerator. And the rest of the thing is independent of t. So that will give you norm of tb by norm of b is equal to 0. So that will imply that since b is non-zero, so this will imply that tb is equal to 0. So this implies also that tb is equal to 0. Now 0 not equal to b belongs to Rn. So t0 is equal to 0. We have seen that, and this is tb is equal to 0 for 0 not equal to b belongs to Rn. This implies t is identically 0. This implies t1 is equal to t. Okay. So the thing is, we have since this, so we have proved that t1 is equal to 0. So this, so whatever, if there exists a t, so that t satisfies star, then t has to be unique, and we define this f prime a is equal to t. Okay. For one dimensional case, we do not prove uniqueness. because the thing is in one dimensional situation a for a function from R to R. So we get derivative by taking a limit of a some quotient, okay? And limit is always unique. For that reason, we don't um, prove uniqueness in the one dimensional. So this is, so let me say this again. So this in one dimensional case we do not prove uniqueness because the limit of because in the one dimensional case you get derivative by taking limit of quotient and limit is always unique. For that reason we don't prove uniqueness. Okay, so let us see. Let us move forward now. Okay, now the next proposition I want to prove. So this thing f is proposition that f is differentiable at a. Okay. Okay, so you have this assumption that f is a. Okay, so let us. Yeah. So you have assumption that that f is a mapping from u to Rn. This assumption you have at a belongs to u. Okay. Okay, so let okay, and then f is, this implies that f is continuous at a. Proof is pretty simple. So you take this thing, let us say this f plus h minus f of a. So this is equal to what? This is equal to f of a plus h, okay, minus f of a. Okay, so before that I forgot to tell you one thing. Okay, so let us hold this thing for a moment. See, the thing is, okay, so decision say you can take this thing. Suppose f is differentiable at a. So what that mean? That means that if you look at this thing, let uh is equal to something like this. F of a plus h minus f of a minus f prime of a h. So this will imply that so f is differentiable at a. This will imply that u norm of uh by norm of h is equal to 0 by definition. Okay. Now this is equivalent to saying that u of h is really little o of h. Okay. So f is differentiable at a. Let uh is equal to really f of a plus this will plus h minus f of a minus f prime of a h. Then the f is differentiable at a. This implies that norm of by norm h is 0 0. So is little o of h. Okay. Okay. So this is the thing. Now, so if f is differentiable at a, so I want to prove that f is continuous at a. So I have to show that if limit h tends to 0, f of a plus h is equal to really of a. So I can write f of a plus h minus f of a by this way, that f of a plus h minus f of a minus f prime a h plus f prime of a h. Now you take the modulus here, modulus here, modulus here. So this will be less than equal to f of norm of f of a plus h minus f of a minus f prime of a h. Applying triangle inequality, I will get this thing. Norm of f prime of a h. Okay, so that is the thing. Now, so this thing actually what? This thing is really your UH. Okay, so this thing is less than equal to. So this thing is the UH. What is UH? UH is the given here. F of a plus h minus f of a minus f prime of h. Okay, so norm of UH. Now this is less than equal to, so this factor, okay, this is less than equal to f prime norm of f prime of a into norm of h. This is the thing. Okay. Now I can write this thing. Okay, here I am using this part that, so if t is a linear operator, t norm of th is less than equal to norm t, less than equal to norm h. Now, so this is really what norm of uh by norm h into norm h plus this f prime a non norm of h. So as h goes to 0, observe that this thing norm of by norm h, this goes to 0, and this is anyway goes to 0, and this, see, a is a fixed number, so this thing goes to 0. Okay, so this, I am calling this vi as h is to 0, since f is clearly RH is of right hand side of vi goes to 0, goes to 0, and what is the reason? Reasons, since what is the reason? Reason is, the thing is f is differentiable. Okay, since reason is f is differentiable. So since this thing, okay, thus okay, since f is differentiable. Okay, okay, this implies, okay, so limit s tends to 0, normal by f of a plus h minus f of a, this is equal to 0. So that means limit s tends to 0, f of a plus h is really f of a. This implies that f is continuous at a. Last issue. Okay, so this finishes the proof of this fact that f is differentiable at a. This implies f is continuous at a. Okay, this is clear. Okay, now we want to really give some example of function, okay, and calculate their derivative. Okay, now one thing you must so before that you just try to understand that. So a little bit discussion. Okay, so okay, so this, so we have proved that if is differentiable at a, then f is continuous at a. So now our goal is to really give some example and a function and calculate their differentiability. Calculate their derivative, total derivative. Okay. Now the thing is, okay. So suppose this little bit discussion. Suppose so f is differentiable at a. So that means this. If you look at this thing, f of a plus h minus f of a minus f prime of h is equal to this thing is little o of h. So that means this will f of a plus h is equal to really f of a plus f prime of ah, and okay, okay, okay. Now the thing is, okay, so this is the meaning of differentiability. Okay. Now, while calculating a derivative of a function, my suggestion is, So I will explain everything. So my suggestion is something like this. The suggestion is use a little low rotation. Second thing is uh, use little low rotation, and second thing is identify the linear map. Linear map, linear map LM. Third thing is ignore the little low part. You will understand what I meaning that. So the thing is, you what you will do, you will express this thing. I am telling that express this thing f of a plus h. You try to express this thing f of a plus h is equal to really f of a plus t of h plus little of. If I can, so you try to express f of a plus h like this part. Okay, okay. Then that will imply that f is differentiable at a, and this f prime of a is t. So this is the thing I want to say. Now the thing is, okay, so sometimes you may really mm, you may confuse with little low notation that so you have to use little low notation very carefully. So so when you are writing a proof or you have to very precise. My suggestion is don't use little low notation in the beginning. You have to use little low notation at the end. Okay, so we'll see what I meant by this thing. Okay, by some example. Okay, so this is the thing, and okay, so uh, let us calculate some example. Okay, so clear. Okay, the first example. Okay. The first example. So let us say I. Okay, so let f is a function from R to Rm with a constant map. With a constant map. Constant map. That is, this implies that fx is equal to c for every x belongs to Rn. Okay, then that will imply that f of a plus h is always f of a, and there is 0 here, so always 0 plus 0, 0 into h and 0. Okay, so 0. Okay, okay, this is 0. So this thus this implies that f is differentiable at a, and f prime a is the zero linear map, right? This is very trivial example. Second example is interesting. Let f R to Rn to Rm be a linear map. Okay. Okay. Now this thing f of a plus h. So since f is linear, this will be f of a plus f of h. Now those who are watching online, so you can pause the video for 1 second and think what will be the derivative of f. Or so the thing is, so this is a zero function. This is 0. So this is definitely little o of h. Okay? Don't confuse with big O notation. So this is little o of h. Okay. Okay. So if you think for a moment that this is that this is exactly in this form, f of a plus h plus f of a plus t of in place of t. This there is a f, right? So derivative of, so this implies f is differentiable at a belongs to Rn at A, and f prime of A is nothing but f. Okay. So derivative of linear map is again the same linear. If T is a linear map, then derivative of T is really T. Okay. So f prime of A is equal to f, for then this is happens for all A belongs to Rn. Okay. The derivative of linear map is again the same linear map. Is again the same linear map. Okay. Now, so example 1, 2, 3. Okay. Let f from Rn to Rn, okay, uh, be given by fx is equal to really fx. This is the identity. So you can guess that derivative is the identity linear operator. Since okay, since okay, so since f is linear by previous case, by case 2, okay, f prime f is differentiable at every A belongs to Rn, and f prime of A is really f. That's clear. Now, okay, fourth thing, let f from so R2 to R be given by f of xy is equal to really xy. Okay. Now, okay, so that A is equal to really A1, comma A2, H is equal to really H1, comma H2. Okay, so the thing. Now this, if you look at this f of A plus H, okay, so this is really f of A1 plus H1, comma A2 plus H2. Okay, so this is nothing but, so A1 plus H1 into A2 plus H2. Okay, okay. Now this is same thing as A1 A2 plus H1 H2 plus, okay, so plus A1 H2 plus H1 A2 plus A1 A2. H1 H2. Now you so now you pause for a moment, and so this is the thing. This is this is f of A plus something like this. Okay. Now, so those who are watching online, they can really pause for a moment and think about the linear map. What is the linear map for a moment? Okay. 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 So okay. So I hope you have got it. Okay. So the thing is, what I'm saying that okay. So if you look at, so let's T from, okay, this R2 to R2, R2 to R be given by this thing R2 to R be given by this thing T of H1 H2 is really A1 H2 plus H2 A1. Okay, A1 H2 plus H1 A2. Sorry, H1 A2. Yeah. So check that. That T is a linear map. Okay. Now the thing. Okay, so one can check that T is a linear map. Now what? So this factor is nothing but T of H1. So this constitutes a linear map. Now remaining thing, this H1 H2. This is a little O of H. So the thing is, if you look at this thing H1 H2, so limit H goes to 0, H1 H2 mod by norm of H. So this is listed H goes to 0. This is H1 and this is H2 mod by norm of H. And this thing, this factor, okay, this is less than 1. So this is limit H tends to 0, norm of H1. Okay, since limit H tends to 0, H, what is H? H is equal to H1 comma H2. That means if H goes to 0, then limit H tends to 0, H1 is equal to 0. Okay, so this is, okay, so that means, so call this as 2, call this as I. So hence from I and 2, and 2, we get this thing that f of a plus h is equal to really f of a plus t of h plus little of h. Okay, okay. This implies f is differentiable at a and a prime of a is equal to t. This is clear. Okay, so now I want to give another example b. Okay. Now I told you one thing. I have okay. So before posting another example, so I have to tell you something. See, the thing is, so you know that. Okay, so I have to tell you one thing. Let B is a. Okay, so let us. Okay, so let us write here. So I have to show that B is suppose B norm B is a. So let B norm B is a normal space NLS. NLS stands for, and suppose dimension of B is really n. Okay. Now under sub identification, you know that B norm B is just under some identification. It's going on. If you under some identification, it is nothing but Rn with respect to some other norm on Rn. So the thing is, if you are able to develop calculus on Rn, okay, then you have developed calculus on any normative space which is of finite dimension. So what I'm saying, let B norm B is a normative space and dimension of B is n. Then B norm B under some identification is nothing but Rn and another suitable norm on Rn. So if you are really developed calculus on Rn, then in principle you have developed calculus on any non-linear spaces where the dimension of that space is finite. So let us go to the thing. Okay, so this is, so how many example IV. Okay, so B. Okay. Okay, so the B thing is Okay, so let okay, so f from MNR to MNR, okay, be given by okay, this fx is this is norm f of x square, x square. This is square. Okay. Now, okay, so we want to calculate the derivative of f. So in principle, you can really see the thing is f is a function from Rm and R. So in principle, you can identify this with Rn square and this side with Rn square. Okay, and so you have to find a linear map from Rn square to Rn square. But my suggestion is not to go into this identification. Instead of that, you directly find an linear map from MNR to MNR. Okay. So what I'm saying, without going through this identification of Rn square with MNR, you just find a linear map from MNR to MNR, and that will be your derivative. Okay, so let us see. So what is okay? So this is okay. So let us start from fx is equal to x then. Okay. So that this is a linear map. So this is a special case of 3 given by fx is equal to x. Since f is linear, this implies this f is differentiable at each a belongs to MNR, a belongs to MNR, and a prime of a is equal to really what? Oh, a prime of a is identity map. That means this implies a prime of a h is equal to h. Okay. Okay. So then B that f MNR to MNR be given by this thing. So f of x is equal to x square. Now what you do, you have to do? You have to write this a plus h square. Okay, so this is f of a plus h. This is really what? A plus h plus a plus h. Okay, so this is the man a square plus ha plus ah plus ha plus ah plus h square. This h square is okay. So this h square is little o of h. This is a square plus ha plus ah little o little o. Okay, so the thing is, so what is that? So you can pause for a moment and think what is the linear map here. So, so let t from MNR to MNR at TA, okay, be given by T A of H is really. Well, let us write T because since A is T of H is really H plus HA. Okay. Okay, so T is stage and this is so thus call this little a from little a of previous position, from a of the previous page, right? We get that thing that f of a plus h is equal to really f of a plus t of h plus little o of h. Thus, we see that f is differentiable at a and f prime of a is t. So f prime of a h is that is this implied. So what does that mean? That f prime of a h is really nothing but a h plus h. Okay. Now the thing is, if f is differential at a means a is the arbitrary point. That this implies that f is differentiable on MNR. Okay, so with this, I would like to stop. Okay, maybe we can do one more example. So let us do one more example. Okay, so yeah, okay, so let us see. That each a belongs to okay. Now the thing is, let us look at another more example. B double I. Okay, so let f MNR to MNR. Okay, so be given by f of x is real xq. Okay. Now the thing is, if you look at this thing, a plus hq, because this is f of a plus h. Okay, so f of a plus h is a plus hq, and this is nothing but a plus h whole square into a plus h. Now this a plus h whole square is something I have written something. So this is really what? Okay, so from a up, this is really a square plus ah plus ha plus little o of h, okay, into a plus h. Okay, so the thing is, this is this. Okay, just one. I will come. Hi. No, just wait for 5 minutes. Okay, so the thing is, this is the thing. So h square plus ah plus ha plus oh into a plus h. Okay. So actually, we will do this. Okay, so let me stop here. We will do this. We will continue from this part. Okay, so in our next lecture. No, let us. Okay, so let us finish this thing. So this a square plus ah plus ha plus oh. So if you will ask this thing, this will be aq. Okay. Then this will be a square h. I am multiplying this thing with this first. Then this will be really aha. Okay. Plus this will be ah square. Okay. This is really ha square. Okay. So this o little o. Okay. So let us stop here. I will. So I have something to do. Okay, so let us stop here it now. So I will continue this in the next lecture. I will continue from this example. Okay, so please subscribe, share, and do like my videos. Okay, so we will see in the next lecture. Okay, so let me stop then.